For 1B, TZ3, and we have both HO and SO. It should be the exact same paper. Again, November 2025. And so we usually have 20 marks for paper 1B, always. And sometimes we can have 3 questions, sometimes we can have 2. This time we have 2. This is 12 marks, and question 2 is 8 marks. And so we have an extra long question 1 here. So let's do this. A group of students is trying to determine the density and viscosity of a liquid. To determine density, they use a balance to read the mass, sphere in air, and immersed in liquid. They use a sphere of volume. The readings are this, and remember, these readings are different due to buoyancy, right? There's a buoyancy force, and we need to draw a diagram to sort of visualize that. Buoyancy force is given by this. We know this formula, and we know these. Okay. State the level of precision in the measurement of m. Okay, so we always use our smallest interval, right? And here they're the exact same because same balance is used. And so we can just immediately state 0.001 grams. They're asking for the level of precision. If they were asking for the uncertainty, we can say 0.00 plus minus 0.001 or 0.0005. They don't exactly tell us whether it's an electronic balance or analog. Either way, I think both of these answers would work for uncertainty. But here we're talking about level of precision, so let's just use this. And so, let's look at B. Show that FB is about 2 millinewtons. So we have a buoyancy force now, and we need to understand how these forces interact, right? You may be thinking, how can the mass be different? And that's because the balance does not inherently know the mass, right? Balance doesn't know mass. It measures normal force that it exerts, right? It exerts a normal force on that object. So let's draw a diagram just to visualize that. We have our balance. Actually, let's just label it balance. Right, and we have our sphere. This is in air. Let's label that air. And we have our, let's use red, or normal reaction force that counteracts our weight. So we have a weight and we have our normal reaction force, right? And so what the balance measures is this. It does not measure the weight. It measures the normal force and then divides by G. And so that's how we get our mass. Okay, and then what we're saying is when it's immersed, let's have a new diagram. So we essentially get two different equations. What's different is when the ball is immersed, now we have a buoyancy force that takes over the normal reaction. We don't have, the normal reaction force does not have to act as heavily. So we have this buoyancy force, Fb, to the same height, same magnitude, total magnitude when we add. And so this is our normal force. It's much smaller because the buoyancy force takes over, and there's still an extra weight to this container, right? So that's why the normal force is still there. And so what we have is our weight. And now we have two different equations. We have a weight in air. Actually, these should be the same, right? Our weight, the weight of the ball should be the same no matter what. What changes is the normal force. And so we have a normal in air is equal to W. We have a normal immersed plus FB is equal to W. And you can visually see that, right? Sum of forces. And so now we have to find FB. Right, and so what is W? Okay, actually, what is N air? M air times G. And this is what's measured by the balance. Measures this. And what is measured by this balance? You get that, right? And so that is M immersed times G plus FB is equal to W. And this W and this W are the exact same. The weight of the ball is always the same. Okay. And so now we can just substitute. We have FB plus, right? I'm using this equation. So we have M immersed G plus FB is equal to M air G. And guys, I'm showing you all the steps just so you understand. So what we get is M immersed G. And so that is just G times the difference between the two masses they have given us. So 1.427 minus 1.208, 1.208, and again that's times 10 to the negative 3. They're both in grams. And let's say 9.8. And let's calculate that. We have 9.8 times 1.427 minus 1.208 times 10 to the negative 3. What we have is 2.1462 times 10 to the negative 3. And what we want to do is write this in 4 SF, right? Although I don't think it is too important in this question, since it's only 1 mark. And so we get 2.146 times 10 to the negative 3, which is equal to 2.146 mn millinewtons, which is roughly equal to what they have given us. So calculate the density of the liquid. Now, density is simply the formula that they've given us, right? We have density here, and we found our buoyancy force. So density is equal to FB buoyancy divided by VG, and that is our 2.146 times 10 to the negative 3 divided by volume, which we found to be 1.827 times 10 to the negative 7 times 9.8. And so what we get, let's put that into our calculator. You guys can do this with me. 1.827 times 10 to the negative 7 times 9.8. And we get 1198.68, right? That's roughly 1. If we put that in 4 significant figures, and we can just simplify that to about 1200. And that should be in, density is simply kg meters, right? And so that's our answer, and we can move on to D. Now for D, we have to determine viscosity. They immerse the sphere in the liquid and drop it from rest. Collect values and plot a graph of position D of the sphere from the moment they drop it. They verify that the sphere reaches terminal velocity after 0.5 seconds. So ideally we should be seeing a curve here, but it looks pretty straight. Draw the line of best fit. Okay, so I don't think we can draw a straight line. And we shouldn't really, yeah. So I think we're looking for sort of a curve like this. But since it reaches terminal velocity, we should have a straight line for most of this. Let me try it. Okay. And so if we go here, it's not going to be straight. If we're here, that's pretty straight. That's pretty straight. Let me start exactly. Okay, never mind. What's okay? Yep. Sorry, glitching software. Okay, that looks pretty straight. Passes through everything, and we could. That also works, but then we have to sort of curve it in, right? So we have that. It's not perfectly straight, and you need to show that curve, right? Okay, outline. Just because it says line doesn't mean it can't be a curve. And so outline how the students may verify that the sphere reaches terminal velocity. Okay, and when we have a straight line, that means our position divided by our time is that's our gradient, right? Is equal to constant. And what is this? This is just our velocity. And so a straight line or constant gradient, right? After uh after what does it say? T equals 5 seconds when reaches terminal velocity. And that should give you that 1 mark. Now we move on to F. They repeat the experiment several times. Estimate an average, and this is our velocity. They use the equation. This is simply our net force equation again, but now there's a drag force. And we have all of this. Radius is given. Calculate the viscosity of the liquid and its absolute uncertainty. Ignore the uncertainties in mass, radius, and volume. Okay, and looking at this, that means the only uncertainty we have is that. So give your answer in the form. Okay, so let's do this. Viscosity. So our viscosity is just m air g. Let's figure that out. We have what's m air 1.427. 1.427 times 10 to the negative 3 g minus, we calculated the buoyancy force as 2.146. So we have 2.146 times 10 to the negative 3, right? And now we have, there's a g here by the way, so don't forget about that. And we have 6 pi, we're given r, 3.52 times 10 to the negative 3. And times our v is just 0.71. So we can calculate that. And I have 1.427 times 9.8 times, sorry, times 10 to the negative 3 minus 2.146 times 10 to the negative 3 divided by 6 pi times 3.52 times 10 to the power of negative 3, and that is times 0.71. And Oops, made a calculator error. Let me just delete that. Okay. And so what I get is 0.2513, right? And that is roughly 0.251. But let's calculate the uncertainty first. So what we have is delta over, right, is equal to delta Vt divided by Vt. And we can have those hundreds or we don't need it. And so then what we can do is find the uncertainty is equal to 0.05 divided by 0.71 times our answer that we just got. And that gives us, calculate that as well, 0.71. And we need to be fast with this in the exam. And what we have is 0.01767. Don't laugh, guys. Okay, being serious here. Okay, and so that's roughly, and we always want to keep our uncertainty in 1 SF usually, unless we have very high precision. And so what we would do is now write our final answer as 0.25 plus minus 0.02. And we need units. Units, let's say, let's actually work this out together. So we have our F is equal to, say, how about we just do this? Is equal to FB divided by 6, right? This is our general equation. And so let's think about this. So F is newtons divided by R is meters, and we have meters per second. And so what we have is Newton seconds times, right? And that is simply kg meters per second squared times second times, and that is just kg second meters, right? So that is our unit. Or we can also just say Newton per meter squared times S, which would be Pascal's seconds, but I don't know if we use that. So I'm going to use this. Right. Okay, and so that's our final answer. And we can move on to G. The students search literature values. So they search literature values and find the viscosity of the liquid to be 0.24. That's pretty close when expressed in SI base units. Suggest a conclusion reached by these students. Okay, so experiment is completely accurate, right? Experimental value is, or let's say experiment is accurate and reliable as the theoretical value falls within experimental uncertainty range, right? Okay, and that was question 1. Let's check our answers. I think I have the mark scheme somewhere right here. Is it here? Yeah. Okay. And so we have question 1A. Let's bring this closer. Don't want to bring it too close in case I flashed it. Okay. 0.01. We got that. Now they are saying you can use this as your precision, but our correct answer would be 0.001. Now we have B 2.1. That is exactly what we did. And so they don't show any stats, so it's quite tough. And we have PVG, so we do get that. See, and they get the exact same answer. That means we know we're right. 0.2146, okay. And now we have, our graph should have a single straight line passing through most points, which does not attempt to pass through the origin. So as long as you're not attempting to pass through the origin, then it's fine. And for the second mark, you need a curved line passing through the first 3 points. Okay, so you need this curved line. So we're right there. And so you could have a curved line from the fourth point as well, as long as it passes through the first 3 points. Okay. So that is correct. Now we have the gradient is constant, the line is straight, terminal V is reached. That is also correct, right? Constant gradient. Or you can say straight line. And now let's bring this down. Oh no, constant. Okay. What we have is, again, they've shown 0 steps. What they want is just the answer. And they have 0.02. Okay. And they have so both of these work. Okay. And so that we got that right. And now we want the value lies within the range of uncertainties, so the experiment was accurate. Yep, that is good. So pretty simple, but some of these calculation questions need a lot of calculation. Yeah. Thank you guys.